In this video, we're going to be looking at some Taylor series free response questions. And I'm going to start with 2012 BC number 6. Okay, this is, overall a pretty straightforward Taylor series free response question. But at the very beginning, they're going to have you use the ratio test to determine the interval of convergence of the Maclaurin series for G. And that's something we haven't done in a while, so I figured I'd just remind you about it right at the beginning. So we know that we're going to need to, in order to run the ratio test, we're going to need to compute the limit as n approaches infinity of the ratio of an plus 1 divided by an and the absolute value of that. Okay, so I'm going to be plugging in n plus 1 wherever I see n in the formula for the general term, right? All of those. Okay, so I'll have negative 1 to the n plus 1. I'm just going to put that in the numerator. Okay, then I'll have x to the 2 times n plus 1 plus another 1. So that'll be, like that. That'll be 2n plus 3. And then over here, when I plug in n plus 1, I'll have 2 times n plus 1, plus another 3. Well, that'll be 2n plus 5 in the denominator. Okay. And then I'll divide by the terms of the original, so that'll be 2n plus 3 in the numerator, and negative 1 to the n, and x to the 2n plus 1 in the denominator. Okay. And so before I do anything else, I'm going to know, okay, wait a second, I'm taking the absolute value, so I don't need to worry about these negative ones. Okay. And then also, okay, I see 2n plus 1 powers of x in the denominator and 2n plus 3 powers of x in the numerator, which is net 2 more powers of x in the numerator than the denominator. So when I cancel them off, I'm going to have, and don't forget your limit notation, x to the 2. Okay, and then I'll put all the stuff with n together, 2n plus 3 over 2n plus 5. And we know that as n goes to infinity, that fraction 2n plus 3 over 2n plus 5 is going to get closer and closer to 2 divided by 2, which is 1. So this limit is the absolute value of x squared. Okay. Now, I know that the absolute value of x squared is equal to x squared for any x, right? So that's just going to need to be less than 1. And, solving this inequality, this is not one that they told you about in Algebra 2 or in Pre-Cal, I don't think. X squared less than 1, well, I might say, okay, there's y equals x squared. There's y equals 1. Where is y equals x squared less than y equals 1? Well, they're between the two intersection points, which is going to be at 1 and negative 1. Or you could think about it numerically. Well, it's a kind of number that you can square and still be less than 1. Well, 0 to 1 would work, but also 0 to negative 1. So I've got, overall, this is going to be negative 1 to 1. Okay? So now that I've got the interior of my interval, I need to check the endpoint. And I'm going to need some more room to work. So I'm going to go over here, and I'm going to say x equals 1. Okay. I've got, what do I have? I think I'm going to just plug in directly into the series. I'll have 1/3 minus 1/5 plus 1/7, and so on. I know the next one's going to be negative 1/9, and then positive 1/11, and I see the pattern. Okay, I know this is an alternating series that is, the terms are decreasing and eventually going towards 0, so I know it's going to converge by the alternating series test. So I'm going to write that in, and I will conclude that the series converges at x equals 1. Okay, so I'm going to take less than or equal to 1. And then I'm going to test x equals negative 1. Okay, and when I plug in x equals negative 1 into the Taylor series, I'm going to have negative 1/3. And then when I plug in negative 1 right in there, negative 1 to the 3rd is negative 1, so I'll have plus 1/5 minus 1/7 plus 1/9, and so on. We see the pattern. Okay, and I'm seeing that this is the exact same thing, it's just the opposite terms are negative from before. So I'm going to say converges for the same reason. And then that would be over there. I mean, it's exactly the same reason. It's alternating. It's still, the absolute value of the terms is still 1 over 2n plus 3, which is a decreasing type of thing, and the limit of the terms is 0. So, I think at this point, we're ready to move on to part B. Okay, now part B is talking about the Maclaurin series for G when evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. Okay, that's a lot. Okay, but I'm just going to point out that pretty much anytime that you read this, you're about to run the alternating series error bound, right? They're telling you that the series converges. That's the alternating series test that I just highlighted in yellow. And so we're going to be using the alternating series error bound. Okay, so using the first two non-zero terms, so I used these two, plug in a half, evidently I get 17 over 120. I'm going to just believe them on that. And I'm going to show that the approximation differs from g of a half by less than 1 over 200. Well, I know that the error in such an approximation, using an alternating series that converges, is no more than the absolute value of the next term, which is going to be this one. Okay? So the error is less than or equal to the absolute value of 1/2 to the 5th divided by 7. Okay? Now, 1/2 to the 5th is 1 over 32. Okay? So I'm going to say that's 1 over 32 and divided by 7. So, okay? And that's less than, 30 times 7 is 210, which is definitely less than 1 over 200. And that's how I'm going to show that the error in the approximation is at most, or is less than 1 over 200. Now, part C is talking about write the first three non-zero terms in the general term of the Maclaurin series for g prime of x. And we're going to be able to do that. We will just kind of go over here and take the derivative of each of the terms. Okay, so g prime of x is going to be equal to 1/3 minus 3/5 of x to the 2 plus 5/7 of x to the 3 minus some other things, but that's three non-zero terms. And then, okay, think about what did I do to each term? And I'll do that to the general term. Well, I didn't change the fact that it was alternating, so that's going to remain -1 to the n. And then x to the 2n plus 1, well, what I did was I brought the power down, reduced the power by 1. Yeah, I made an error there. It's definitely a 4, right? Yeah, 5/7 x to the 4th, reduce the power by 1. Okay. And we're going to divide by 2n plus 3. Because I didn't change the denominators. Okay, and that's the general term of the Maclaurin series for g prime. There we go. Oh, it wasn't so bad. Next, I want to talk about one from 2011. And this one, we've actually already done parts A, B, and C at an earlier point in this unit. This is the one where it was talking about sine of x squared and cosine of x. You can see that. And we wrote down the Taylor polynomial for it. We found what the value of the sixth derivative of f at x equals 0 was without actually taking 6 levels of derivative. And so now we're going to do the Lagrange error bound part, right? And this one, it doesn't say use the Lagrange error bound, but I think the hint is right here where it says, hey, here's the graph of y equals the absolute value of f's fifth derivative. There's no other reason in AP Calculus why we need to look at the graph of the absolute value of a high-order derivative besides running the Lagrange error bound. So what we're going to do is we're going to say, all right, I know what to do here. We know that we're trying to show the error, that's what this thing represents, is less than 1 over 3,000. Well, I know that for a Lagrange error bound scenario, I'm going to work off to the side. Error is bounded by kind of the next term. Well, if I used a 4th degree Taylor polynomial, then it's going to be the 5th power term. So it's going to be the maximum of the absolute value of f's 5th derivative over the interval 0 to 1/4, because we're centered at 0 and we're plugging in x equals 4th. Okay. Divided by 5 factorial times the absolute value of what are we plugging in? 1/4. We're centered at 0 to the 5th power. Okay. Now we're going to look over here and we're going to say, all right, this is 1/4. And so we're really only looking at this graph between these two vertical lines. And I know that between 0 and 1/4, the graph is below y equals 40 the whole time. Right? I told y'all when we were learning about the Lagrange error bound, the number you pull from a graph is always printed there on the graph. Right? You don't have to say, oh, that looks like 37 or something, because you don't know it's 37. Okay? But you know it's below 40 because you can see that little bit of, see if I can, remove that and this. You can see that little bit of space between the curve and the horizontal line that represents y equals 40. Okay. So now I'm going to plug in 40 for the maximum possible value of f's 5th derivative. I'm going to divide by 5 factorial, and I'm going to have a 1/4 to the 5th. And our job now is to show that that's less than 1 over 3,000, and we're going to be able to do it. Okay, I'm going to say 40 is 5 times 4 times 2. And then 5 factorial is 5 times 4 times 3 times 2. And then I'm going to leave that 4 to the 5th right there. I'm going to start canceling some stuff off. And so really now I've got this 3 in the denominator, and it's like, okay, this 4 to the 5th, I need to be able to show that that's like basically 1,000. And I think the way to do that is to rewrite this 4 as 2 times 2 to the 5th. If I take that 2 times 2 5 times, I'm going to have 10 total powers of 2. Okay. Down below, I listed out the powers of 2, right? It goes 2, 4, 8, 16, 32. 2 to the 5 is 32. We already saw that once in this video. And then 64, 128, 256, 512, and 1,024 is 2 to the 10th. So I'm looking at 1 over 3 times 1024, which is definitely less than 1 over 3,000. Now I want to look at another problem from 2011. This was from the Form B exam, but I like this one. This is a good one. So we're going to, they give us the Maclaurin series for log of 1 plus x, and we're going to use that series to write the first 4 non-zero terms and the general term of the Maclaurin series for f, which is log of 1 plus x to the 3. Now if I go over here and I look at, the difference between this function and that function, really what I've done is I've just replaced x with x to the 3. So that's exactly what I'm going to do in the Maclaurin series. So the Maclaurin series for f, okay, first 4 non-zero terms and the general term, so f is going to be, okay, replace x with x to the 3. That's supposed to be a minus. So say minus x cubed squared over 2 plus x cubed over 3 minus x cubed to the 4th over 4. Right, and all I'm doing here is replacing x with x to the 3. So plus negative 1 to the n plus 1, x cubed to the n divided by n. And that's going to be a safe place for us to stop. But I just remembered, because I worked this problem in class repeatedly, that it actually pays off for us to simplify this, or at least the first 4 non-zero terms. So I'm going to call that x to the minus x to the 6 over 2 plus x to the 9 over 3 minus x to the 12 over 4, and so on. And I should probably put a dot on it. Right. Now in part B, they're going to give us the radius of convergence and ask us to determine the interval of convergence. Okay, so really this is kind of like that one I did earlier with the ratio test, except I don't actually need to run the ratio test. They already did that for me. I know that this is a Maclaurin series, so it's centered at 0. And if the radius is 1, well, then it's going to reach out to positive 1 and back to negative 1. Okay, at least the interior of the interval. Now we have to check the endpoints, but that shouldn't be too bad, right? I should be able to say, all right, when x is equal to 1, I've got 1 minus 1/2 plus 1/3 minus 1/4, and so on. Okay, this is the alternating harmonic series. It is an alternating series, but it's the alternating harmonic series. And we know that the alternating harmonic series converges. And we know it converges conditionally, but that's still converging. Okay, so we know just from what we know about interval of convergence that on the interior of an interval of convergence, the series is always converging absolutely. We've just determined that it converges over here at x equals 1, so really the work that remains is to see what's going to happen at x equals negative 1. Okay, when I plug in x equals negative 1, I'm going to get, well, negative 1 to the 3 is negative 1. Negative 1 to the 6 is going to be positive 1, so I'll have minus 1/2. And, well, x to the 9, when x is negative 1, that'll be negative 1 over 3. And then x to the 12, same story. It's always going to be negative. Okay, so minus dot, dot, dot. Okay, this is a harmonic series. It's negative, but I'd say it's still harmonic. And we know what the harmonic series does, pardon me. We know it diverges. Okay, so it's not going to converge at that endpoint, meaning my interval of convergence is -1 is less than x, which is also less than or equal to 1. Now in part C, they're going to ask us to write the first 4 non-zero terms of the Maclaurin series for f prime of t squared. And it's like, okay, that's a little unusual. Okay, so what I'm going to do is I'm going to kind of take this in 2 bites. First, I'm going to take f prime, and then I'm going to plug in t squared for x. Okay, so I'm going to start with, all right, f prime of x is going to be 3x squared minus 6 divided by 2 is 3x to the 5 plus 9 divided by 3. That's weird. 9 divided by 3, x to the 8 minus 12 divided by 4, x to the 11. I don't know that I've actually worked this part of this problem before. This is unusual. I didn't expect that. Write the first 4 non-zero terms of the Maclaurin series for f prime of t squared. Okay, so now what I'm going to do is I'm just going to, okay, I might write a ... But I'm going to say, all right, t squared is t to the 4, so that's 3t to the 4. Okay, minus 3, when I put in t squared for x, I'm going to get t to the 10, plus 3 times t to the 16, and minus 3 times t to the 22. All right? Use the first 2 non-zero terms of the Maclaurin series for g to approximate g of 1. Okay, well, g is an antiderivative of f prime of t squared. Okay, probably best we don't try to figure out what it is explicitly in terms of f. I don't know that you actually can write down a formula for it in terms of f. But g is going to be an antiderivative for f with respect to x, and we're going to use the first 2 non-zero terms of the Maclaurin series for g. Okay, we know that the first, hold on, what am I saying here? Yeah, the first term is going to be 0. G of 0 is 0 because, the interval from 0 to 0 of anything is going to be 0. So I know that g is going to equal, okay, anti-differentiate, I'm going to add 1 to the power. And then, we're going to plug in x eventually, so I'll go back to x's. Divide by the new power. Okay, minus 3 over 11, x to the 11, and so on. Okay. That's the first 2 non-zero terms of the Maclaurin series for g to approximate g of 1. Well, I'd say, all right, g of 1 is going to be approximately equal to 3/5 of 1 minus 3/11 of 1. Okay, and so that's just going to be, it's just going to be a number. All right, now part D is, okay, the Maclaurin series for g evaluated at x equals 1 is a convergent alternating series with individual terms that decrease in absolute value to 0. Again, this is a hint that you're about to run the alternating series error bound. So I'm going to show that my approximation I just made must differ from g of 1 by an amount less than 1 over 5. All right, well, I'm going to do the error bound. So the alternating series error bound says that the error is less than or equal to the absolute value of the next term. Okay. Which is to say, well, I might need to do a little bit of work here. Think about what the next term would be. That'll be positive 3 over 17 times x to the 17, right? You could also probably just see it from the pattern, not looking at the terms of f prime of t squared. But, the power increases by 6, and it's 3 divided by the power times x to the power. Right? So it's going to be 3 over 17 x to the 17. And then when we plug in x equals 1, I'm going to say, all right, well, that's the absolute value of 3 over 17 times 1 to the 17th power. And that's, let's see, make this a little smaller without bringing in part of another problem. Yeah. Okay, which is just, 3 over 17. Well, 3 over 15 is 1/5, so I'm saying that this is less than 1 divided by 5. Now, the last one I want to work with you is from 2007. This is a good one, because it's got something just like different from what else I've done in this video. So it's got the known Maclaurin series, e to the x. We're going to use that to write the first four non-zero terms in the general term of the Taylor series for e to the negative x squared around x equals 0. So, all right, we already know that e to the x equals 1 plus x squared over 2 factorial. We need four non-zero terms, so that's plus x to the 3 over 3 factorial. We're going to need a general term eventually, so I'm going to write that in as well. We know that's n over n factorial, and it keeps going. Okay. That means that e to the negative x squared is, I'm just going to replace x with negative x squared. Well, that'll be a negative x squared. When I square negative x squared, I'm going to get positive x to the 4. Okay, when I cube negative x squared, I'll get negative x to the 6th. And then I'm just going to call this negative x squared to the n divided by n factorial. And I have written the first four non-zero terms and the general term of the Taylor series for f around x equals 0. Now we're going to use our answer from part A to find the limit as x approaches 0 of 1 minus x squared minus f divided by x to the 4th. And you might be looking at this to me like, wait a second, I feel like I could do this myself. Like, it's going to be a L'Hopital rule question, right? But think about how that would play out. You know, you take the derivative at the top and you get negative 2x minus f prime. That'd be easy enough to compute. We can compute f prime of x. But then we have 4x to the 3rd in the denominator. And as x goes to 0, I'm still having a 0 in the denominator. And, you know, presumably, you know, if this limit's going to exist, I'd have to do L'Hopital's rule 4 times. And that in and of itself wouldn't be so bad. It's the taking the fourth derivative of f by hand that's really going to be time consuming. Because at first it's just chain rule. And then it's product and chain rule. But then it's product and chain and product. Or, you know, it just gets worse and worse. So we're not going to want to do that. What we're going to do instead is we're going to say, let's just think about what's going to happen with 1 minus x squared minus f. Let's say 1 minus x squared. Maybe I'll put that in brackets. Then I'm going to subtract f. Well, that would be 1 minus x squared minus this one and minus that negative x squared. Okay, so I'm just going to lose both of those first two terms, right? If I have 1 minus 1 and negative x squared minus negative x squared, well, those just give me 0. So I'm going to have x to the 4 over 2 factorial minus x to the 6 over 3 factorial, plus a bunch of stuff that's got higher and higher powers of x, right? And that will be important later. Because when I go and I divide this by x to the 4, well, each term will get divided by x to the 4. We've done this type of thing. So I know that I'm going to divide this by x to the 4 and I'm going to get 1. I'm going to divide x to the 6 by x to the 4 and I'm going to get x to the 2. I know that the rest of the terms are going to have even higher powers of x than x to the 6, so that when I divide them by x to the 4, I've got more than 2 powers of x, which is to say that when I plug in 0, I'm going to get a bunch of zeros. Okay? So I'm going to say that the limit as x approaches 0 of 1 minus x squared minus f of x divided by x to the 4 is going to equal 1 over 2 factorial. Wait a second. I forgot I was subtracting f, right? So that needs to be negative, and that's going to need to be a positive and the rest of them, right? Because when I'm subtracting f, I'm subtracting this x to the 4 over 2 factorial, subtracting that negative x to the 6 over 3 factorial. And so I just got the signs off a little bit. But that'll be a plus a 0 minus 0 plus, you know, a bunch of zeros. Which is to say that, you know, that's going to be equal to just negative 1/2. No, it's something very different from what we've seen so far. Part C says, okay, we're going to write the first 4 non-zero terms, not the general term, for the integral from 0 to x of e to the negative t squared dt. All right, so it's just going to be an antiderivative for f, right? And so we're going to say that that's going to be okay. I know that anytime I run an antiderivative, I'm going to incur a plus c. Then I'm going to have 1x, and I'm just going to kind of start adding 1 to the power and dividing by the new power. So that's x to the 3 divided by 3, x to the 5 divided by 2 factorial. So x to the 5 divided by 5 and 2 factorial, I guess is what I meant. minus x to the 7 divided by 7 and 3 factorial. 3 factorial is 6, so that would be 42. And I know, well, that'll be at least 4 non-zero terms. That'll be enough. Okay. Now I got to think about, you know, what happens when x is equal to 0 on the integral. Okay, when I plug in x equals 0 right there, I need to get back 0 for my integral. So I need to be able to do the same thing over here. When I plug in x's here, I'm just going to get a bunch of zeros, which means that I need to get in total 0. So that means c has to be 0. So I'll just kind of move this over. Maybe I'll indicate dot, dot, dot. Say, I know it's going to keep going, but you only asked me for the first 4 non-zero terms. You didn't ask me for the general term, so we're just going to say, like, there it is. Okay, use the first 2 terms of my answer to estimate the value of 0 to the integral from 0 to a half of e to the negative t squared dt. All right, well, so 0 to 1/2 e to the negative t squared dt is going to be approximately equal to 1/2 minus 1/2 cubed divided by 3. And we don't need to simplify that. There's not going to be any benefit to simplifying that. We're just going to stop there. Now in part D, they're going to ask me to explain why this estimate I found in part C differs from the actual value of the integral by an amount less than 1 over 200. Okay, that's going to need to be an error-bound situation. And I've got an alternating series, so I know it's going to be the alternating series error-bound. Okay, now since they didn't say the special words for me, I'm going to check the conditions. You didn't need to see me write that, so I'm saying the Taylor series estimate for that integral alternates, decreases in size, or the terms are decreasing in size. So I might say has terms that decrease in size. Let me get rid of that S. I don't know. That decrease in size and go to 0. Okay. That means I can use the alternating series error bound. So I know that that means that the error in that approximation is going to be no more than the absolute value of the next term. Well, that next term would be that x to the 5 divided by 10, right? So it's going to be the absolute value of 1/2 to the 5th divided by 10. And I know that 2 to the 5 is 32. So I'm going to say that's 1 over 32 times 10 is 320, which is definitely less than 1 over 200. Okay, so I think that was a good selection of Taylor series free response questions. If there are more examples of Taylor series free response problems, I've got a list of them compiled, and I guess I'll link that in the description. You should definitely try the problem set, the homework 12.4 that I've got for this topic. That's got more examples. But that'll be all for this video. Thanks for watching.